Alright, so we're going to cover some properties of real numbers and then simplifying expressions. So before we start, let's talk about what real numbers are. So real numbers are all of the numbers that we deal with in this course, at least for a while. And there's different, what we call subsets of real numbers. So the natural numbers are the numbers that we count with. So our basic 1, 2, 3, 4, 5, 6, etc., etc. So we're just going to call these our counting numbers. And these are always whole numbers. Yeah. And then our integers that's where we include positive and negative numbers, and 0. So positive or negative whole numbers. So, in these examples here, notice I included 9 divided by 3 as a natural number because 9 divided by 3 is 3, which is a whole number. And square root of 25, that would equal just 5, so that's also a positive whole number. So, the rational numbers are a little bit more of a complicated definition. So, a rational number formally is any number that can be expressed as a fraction of integers. So that of integers part is extremely important. So a number like pi over 2 would not be, because pi is not a rational number. But all these numbers here in our examples can be written as fractions. 5 is also 5 divided by 1. 7/12 is obviously pretty straightforward in our definition. 0.29, well, that means that's 29 over 100, 29 hundredths. And similarly, 0.3 repeating, that equals exactly 1/3. And then the rest of these numbers are called irrational, meaning numbers that are not rational. So numbers that cannot be expressed as a fraction with integers. Interesting thing about irrational numbers is in the ancient times, so going back to the ancient Greeks, the first guy who proved the existence of these irrational numbers was actually thrown overboard and killed, because the ancient Greeks thought that math was this perfect and clean, nice thing, and that all numbers should be able to be written as perfect integer fractions. So this guy who came along and actually proved that numbers like square root of 7 could not be written as a fraction exactly, was considered a heretic and thrown off of a ship. Fun fact. All right. So commonly, these sets of numbers are, we see this diagram. It pops up in a lot of places. And what this is showing, it's like a Venn diagram. So we're saying that all of the natural numbers are contained within, and the whole numbers, I don't really talk about those, but it's just the natural numbers including 0. But we're saying that all of these natural numbers are contained inside of this box that has only integers. And all of these integers are contained in this box that has all of the rational numbers. And then notice the irrationals are separate because they're not rational, so they're also not any of these other things. And then this entire thing falls inside the realm of real numbers. So all of the rationals and the irrationals make up the real numbers. And later in the course, we'll talk about this other set of numbers called complex that are not real. They exist, they're just considered not real by the mathematical definition. So let's talk about applying this definition. So identify the sets to which each number belongs. So 5 maybe I shouldn't have picked exactly in a number that was already on the sample, but or in the example, but we know that this is a natural number, and therefore it is all of the things above natural numbers in that diagram. So it's also a whole number, it's also an integer, it's also a rational, and it's also a real number. By the way, these sets actually have an abbreviation. So the natural number set is commonly written as, it's an n but with an extra line, and then the integers are commonly written as a z with an extra line. I have no idea why it's a z, but that's just what we do. The rational numbers are written, of course, as a q with an extra line. This one I do know, the q stands for quotient, and the reals are written as an r with an extra line. So these are abbreviations that we'll commonly use. So, okay, so 3.7863. Again, this one's can trip people up, but this 0.7863, this is a decimal, but it just stops right there. So we know that the 0.7863 would be out of 10,000. So this is the same as 3 and 7863 out of 10,000. So like the mixed fraction, which makes it a rational number. So in this one we would have q, and then also it's a real number. And lastly, square root of 12. This one is irrational, which I think people actually do write this as an I with an extra line sometimes, but it looks weird. And it's still a real number. So these numbers that cannot be written as fractions are still in fact real numbers. Just don't go telling any ancient Greeks that, or you might get thrown off of a ship. Yeah, and in fact, any square root of a number that's not a perfect square, so we know numbers like 9 and 16 and 25 are perfect squares because they have a natural number answer. Any number that's not one of those numbers, so square root of 12 is not a rational number. Cannot be written as a fraction. It will have, so another thing about these numbers is they have non-repeating, non-terminating, decimal expansions. So when you type square root of 12 in your calculator, you'll get a really long decimal answer, and it won't follow any specific pattern. So that's what an irrational number is also. All right, so moving on to the next page. These are some properties that apply to all of the real numbers. The thing about these properties is they have fancy names, and they're written in these algebraic symbols right here, but they say things that you already know. These are considered our starting points for all of math, really, especially algebra. So these are the things that we assume to be true about numbers, and we hope that they are always true, and they should always be true, because they're just common sense things that make sense. So you can change the order when you add or multiply things. You can change the order. Or in the second one, the associative property says it doesn't matter how we group. So if I were to add A plus B and then add C, it's the same as adding B plus C and then adding A to the result. The identities is just saying that there's the existence of this number, that when I add it, it doesn't change the results, or we call 1 the multiplicative identity, so 0 is the additive identity. Inverses is saying that there's always a number I can add to get 0, and there's always a number I can multiply by to get 1. And the distributive property is the one that says I can do this, right? If you think about your order of operations, the distributive property is really what says that multiplication can come before addition. commonly referred to as that PEMDAS abbreviation. But it's saying multiplication can happen before addition. Notice that combining like terms is not actually one of these what we call axioms, these properties of real numbers, but it's actually just an application of the distributive property. So if we were to take a very common mathematical phrase, 3x plus 2x. And what we're going to do here is we're going to use the distributive property but going backwards. So normally you're used to going this way with the distributive property, but it can also be used to go this way. So I could take the a out and make it a times b plus c. And that's what I'm going to do here. I'm going to take the x out, I'm going to undistribute the x, and now I have x times 3 plus 2. And you can see that 3 plus 2 is pretty obviously 5, x times 5, which we would usually write as 5x. So you've been applying these properties your entire mathematical life, but not always referring to them by name. I don't usually care whether or not you guys know the names, but you should be able to apply them in many different ways. All right. So lastly, let's do a couple examples to reinforce these ideas. So when we simplify expressions, this is something, again, that you do a lot without really thinking about what you're doing. When you simplify an expression, you're just finding a simpler way to write the exact same sentence in math. So here we're going to evaluate. So evaluate means I'm going to substitute in 2 for A and negative 3 for B. So first let's evaluate the expression. So I would have 3 times 2, and then parentheses 2 minus 5, plus negative 3 times 2, 2 times 2, because A is now 2, and then minus 9. And if we're careful with our order here, we would have 3 times 2 is 6. This is going to be 6 times negative 3. And then this part will be 2 times 2 is 4. 4 minus 9 is negative 5. So that's going to be minus 3 times negative 5. And then this would come out to negative 18 plus 15, which is negative 3. So now we're going to take a step back and we're going to simplify the expression. The point of evaluating it first was we're going to use this to check our work. So now let's write out the original expression again. So it was 3a times a minus 5 plus b times 2a minus 9. So now we can apply the distributive property, so 3a times a and 3a times negative 5. So 3a times a, we could write that as 3 times a, but we like to use as few pen strokes as possible when we write in math. So we have a shorthand for a times a, and we know that that is the same as a squared. So that's 3a squared minus 15a plus, and then we can distribute here. So b times 2a, b times negative 9. b times 2a are not like terms, but we can still write them as though they're multiplied, and we usually like to write things in alphabetical order. So 2ab, so 2 times a times b, minus 9b. And now we look and see if there are any like terms to combine, but sadly there aren't, because this is a squared, and a squared and a are not the same kind of term. So none of these things are like terms. But now let's go ahead and evaluate again. And this is going to help us make sure that we did it right. So again, we're going to substitute in 2 for a, negative 3 for b. So we have 3 times negative 2 squared minus 15 times negative 2 plus 2 times negative 2 times 3. Oh no, that's a positive 2. So 2. Oh, the whole thing's positive 2. There we go. Positive 2's. 3 times 2 squared minus 15 times 2 plus 2 times 2 times negative 3 minus 9 times negative 3. And if we do this correctly, so 2 squared is 4 and 3 times 4 is 12. Negative 15 times 2 is negative 30. And then 2 times 2 is 4. 4 times negative 3 is negative 12. And then minus 9 times negative 3 is minus 27. Plus 27. 2 negatives make a positive. And this actually all does come out to negative 3. So we got the same answer before we simplified and after we simplified. So we know we did this right. And you could check your work if you pick any pair of numbers and substitute them in before and after you simplify. And if you did it right, you'll always get the same answer. All right, so another example. Again, let's try substituting in first, and then simplifying, and then substituting again. So 3 times 2 plus 4 times negative 3 minus 2 times negative 3 times 5 minus 2. So careful with the order of operations inside the parentheses. So 4 times negative 3 is negative 12, and 2 plus negative 12 is negative 10. And then that's a minus, not a times. Minus 5 minus 2 is 3. So, and negative 2 times negative 3 is now positive, so we can make this plus 6 times 3, which is negative 30 plus 18, which is negative 12. Okay, so now we can simplify. So rewrite the original expression. And again, we can apply the distributive property to get 3a plus 12b, and then distribute the second part, being careful to also include that it is in fact a negative 2b, so that's the whole thing that's being distributed. So we get minus 10b, and then negative times negative makes plus 2ab. And then here we do have like terms we can combine. We have 2b terms. So 3a plus 2b plus 2ab. And one thing we see when we simplify is it's usually easier to evaluate an expression after it's been simplified. Not always, but usually it is. So if we now substitute in 2 for a, so 3 times 2, negative 3 for b, 2 times negative 3, and again 2, negative 3. And wouldn't you know it, we get 6 minus 6, and then minus 12, which comes out to just negative 12. And there it is. The end.